In this video, we're going to explain how to find a basis for the column vectors. The key is to use the elementary row operations. Now, the following theorem explains how the row operations affect the column space of a matrix. So suppose we're given a matrix A, then the elementary row operations typically change the column space of A, but they preserve linear relations or relations of linear dependence between columns of A. What does that mean? So suppose A has column C1, C2, all the way to Cn. And suppose we had a linear relation or linear dependence relation. That means that some number x1 times c1 plus some number x2 times c2 plus some number xn times cn is equal to the zero vector. And then what this is saying is that if we do an elementary row operation, which corresponds to multiplying the matrix A on the left by an elementary matrix, or in another way of saying this, it corresponds to interchanging rows of A, multiplying a row through by a non-zero scalar, or replacing a row by adding to it a scalar multiple of another row. Now we get a new matrix then with columns C1 primed, C2 primed, and so on up to Cn primed. Then the same linear relation x1 c1, xn cn holds. This x1 here is the exact same x1 here times c1 primed. This is a new column, not the same column that was originally in A, plus xn times cn primed is equal to 0. That's the then part of the statement. So what this is saying is that as a consequence, the elementary row operations preserve linear dependence and linear independence of the set of columns of a matrix. The proof is quite simple. So the linear dependence relation x1 c1 plus x2 c2 and so on up to xn cn equaling 0, that translates very compactly to this equation A times x equals 0, where x is this n by 1 column vector made out of x1, x2, all the way to xn, and A is the matrix consisting of the columns. Okay, and so then if we have this equation, that was our hypothesis, and then that translates to Ax equals 0. And if Ax equals 0, then multiplying both sides of this equation by the elementary matrix E, we get E times Ax equals E times 0, which is 0. And so therefore, we conclude E times Ax equals 0, and that means this equation is true. Now let's finally do a concrete example. So let A be the matrix given here. Find a basis for the column space of A. Again, the column space is the span of all these columns. And so there's, I think, 7 columns here. And these columns sit inside a 4-dimensional space R4. So there's too many of them. We don't need all of them to span this column space. We only need, well, at most 4, but there might be less. Okay, so the solution is just find the reduced row echelon form of A. So in SageMath, the command is like this, a.ref parentheses. And so we get this. Of course, doing this by hand is, quite tedious. We practice that a lot in chapter 1. Okay, so then step 2 is identify the pivot columns of the reduced row echelon form of A. So I've boxed them in red here. What makes them the pivot columns? They're the leading ones of each row. So, like for example, in row 3, 0, 0, 0, and then we hit a 1. In row 4, there's no leading 1, so no pivots. Okay, so you can also ask Sage what are the pivots, and Sage returns these numbers 0, 1, and 3. Now, Sage starts counting starting from 0. So this is column 0, column 1, column 2, and column 3. So these are the columns where the pivots are located. Now, a fairly obvious fact is that these columns form a basis for the column space of the reduced row echelon form of A. In other words, for this matrix. These columns here do not form a basis for the column space of A. That's what we're trying to find out. But the good news is that the corresponding columns of A form a basis for the column space of A. What do I mean by that? So recall that we're looking at the columns in positions 0, 1, and 3. If we add 1 to each of these, that means columns in positions 1, 2, and 4. So that's what I've highlighted here. This is the original matrix A, not the reduced row echelon form of it. And then what this answer is saying is that these highlighted columns are the answer. And the reason is the theorem we proved on the previous slide, that the linear independence of columns of a matrix is not changed by doing elementary row operations. So we started from this matrix A, did a bunch of elementary row operations, and got to the reduced row echelon form of A, and we saw that columns 1, 2, and 4 in the reduced row echelon form were linearly independent, and therefore columns 1, 2, and 4 in the original A are going to be linearly independent. And the same statement holds with spanning and basis replacing in place of linear independence. Let's ask Sage to check this. So here is just the command for this asks to take this matrix A, and for I in A dot pivots, so I being 0, 1, and 3, let's just print this is an arbitrary row, comma, column 0, column 1, column 3. So an arbitrary row with in position 0, that's this thing here. So that's why the first output is the first column. Now Sage treats, when I turn this into a vector, it makes it a row vector, makes this column a row vector. That's okay. And then similarly in column with I equals 1, we get the second column printed out, and then I equals 3, we get the third or fourth, depending on how you're counting, column printed out. Okay, so this was just how to just extract these columns from this matrix A. You use this command or notation here. Okay, let's throw them into a list, L. And so that's what I've done here, using Python, how to make lists in Python. Okay, so here's our list. It's simply these vectors put into a list. And then I can ask, what is this, or I can construct this vector space span of L and ask, is it equal to the column space of L? And the Sage says, yes, that's true. And then I can also ask, are these vectors L in L linearly dependent? And to do that, I need to say that, okay, I'm working in the space Q to the 4th or R to the 4th, because these vectors here have 4 components, so they're in R to the 4th. And are they linearly dependent? If they are, they won't form a basis. And fortunately, or as expected, they are not linearly dependent. And so that's why Sage is returning false. They're not linearly dependent. That means they're linearly independent. And then they also span the column space, and therefore they form a basis, because a basis is a set of vectors that span and is linearly independent. To summarize, the final answer is the highlighted columns that you get from looking at the pivot columns of the reduced row echelon form of A. This is not the actual pivot of the reduced row echelon form, but the positions of those columns, and then you look at the columns in A, and that will be your answer.